Okay, we're looking at applying the model, the second page. Now we're going to look at the two problems for which CAPM applies, and we are going to illustrate the situation with three graphs and a diagram. So the first one will be problem 1, where we have a car, or a truck rather, speeding up from rest to 20 meters per second. So I'm going to draw my velocity graph first because that's the information we're most directly given. So my V and my T. So I start at rest, it tells me, and then I reached 8.5 meters per second at 20 seconds. Because it's CAPM, that's going to be a linear graph. My acceleration as a function of time. This is the slope of the V graph. That slope is constant and positive, so I'm going to have a constant positive acceleration. The position graph. The velocity value is the slope of the position, so I should have a graph that starts with a 0 slope. It doesn't matter where I start it, so I'll just start it here for fun. But it needs to start with a 0 slope, which means it needs to start out flat, and then the slope needs to increase to a more and more positive slope, so something like that. So it should be a smooth curve all the way around. That flat spot is only at a moment. It's not for like a duration. And a diagram which would explain that. So we have our truck starting with an initial velocity of 0, so I label that. At the end of the interval, it's some delta x down the road, which I don't know, but it did take 20 seconds. The VF is 8.5 meters per second, and the acceleration over this interval is to the right, though I don't know the magnitude. Because it's speeding up to the right, so the acceleration must be to the right. Okay, problem 3 is my next CAPM one. We have a truck slowing down to a stop. So I'm going to draw my X in there first so that I make sure I don't lose it. So I'm starting at 8.5 meters per second. Oh, I wrote 20 up there. This is 8.5 meters per second. It's about 20 miles an hour. And over the course of 20 seconds, I go from going that fast to being stopped. Again, a linear graph because it's CAPM. The acceleration now will be negative because the slope of this graph is negative, and the slope is constant, so the acceleration value is constant. The position graph should have a high positive slope to begin with because the velocity has a high positive value. And at the end, the velocity is 0, so the x graph should have a 0 slope, so it should be flat. So something like this. And I can start that anywhere I want to on the axis. What's important, though, is that I have a high positive slope that gets smaller and smaller until the end. And this one's a car with an initial velocity of 8.5 meters per second. I'm calling positive to the right, as I did up here. And its final velocity is 0. Delta x is unknown. The delta t is 20 seconds. The acceleration this time is to the left because I'm going to the right and slowing down, which means my acceleration and velocity have to be opposing each other. So notice on these two diagrams I drew the object at the beginning and the end, and I labeled along the interval the delta x and the delta t. I labeled the vi and the vf with vectors if they're not 0, and I labeled the acceleration vector and the direction of positive. Those are the things that need to go into your diagrams. So, problem 2 was where CVPM applied, and we had a buggy driving at a constant speed of 8.5 meters per second, which means the acceleration is 0. And the position graph should have a constant positive slope because this has a constant positive value. And this is a little easier to draw because we have fewer quantities to label. So the v is 8.5 meters per second at the beginning and the end. delta x is unknown, the delta t is again known, and the acceleration is 0.